Okay, so here is the long-awaited video for packet B1.2, which is proteins. Oh my goodness. It is Thursday. I filmed this yesterday. Tried to upload it. It said the file couldn't process. I thought it was like an internet issue or something. No, apparently it was a file issue. I don't know. Anyway, this is now the third one of these packets I've done, but it's okay. It'll be fast. So, 4 levels of protein structure. I feel like we've been over these pretty in depth at this point, but there's a couple of notes that I think are important. And so, key things, there's a difference in how the structures are determined between primary and then pretty much the other ones. So, primary structure, primary structure is only determined by amino acid sequence. So unlike the other ones, your primary structure is just the sequence of amino acids. It has nothing to do with the bonding or the shape. It is strictly just what amino acids are in it and how many of them there are and what order they're in. Your secondary, tertiary, and quaternary structures depend on some of the factors that are around the protein. I was having this conversation with someone earlier today. And so your secondary, secondary, tertiary, oh, that's okay, and quaternary structures. Couple bullet points. So, affected. Should it be affected or effected? I should have written impacted. Oh well. Affected by temperature. pH. Polarity of solvent. Presence. How do I spell presence? Okay, that's supposed to be presence of metals. That is wrong. I can tell that's wrong. I'm sorry. So all these things can impact folding. We looked at that with our albumin. We saw how they changed the different structures, how they can be denatured. Sometimes it's not a full denaturing. Sometimes it can just be a shift in structure. And so anytime that there is a difference in the conditions around it, it's going to change secondary, tertiary, quaternary. It is not going to change primary unless the protein is being like ripped apart because it's like that severe of a condition. They also typically form whatever their end structure is. So if it's going to stop at a secondary structure, it'll become a secondary structure and then stop. If it's going to stop at a tertiary structure, it'll get to tertiary structure and then stop. If it's going to form to a quaternary structure, it'll get to that structure and then stop. Like they happen like all at once. It's not like it will grow over time. It's not like it's born as a primary structure and then it grows into a secondary structure, and then it grows into a tertiary structure, and then it grows into a quaternary structure. It like is or it isn't, if that makes sense. So form, shape, spontaneously. Why can I spell that but not presence? I don't know if I spelled that right, so maybe I'm tooting my own horn when I shouldn't be. And so primary structure. Primary structure. What comes next in the rainbow? I guess yellow. I don't have orange. Secondary structure. And then tertiary structure gets to be green, my favorite. And then quaternary structure can be blue. This matters to only me. I'm sorry. Alrighty, so on to primary structure. And we'll go through them in like sequential order because that just makes the most sense. So what is the primary structure of a protein? Where's, not this one. What color is that? I tried to get red, but it looks more like pink. So we'll write it in pink. And so primary structure of a protein is the sequence, which just refers to the number of and order of amino acids oh geez. Oh. And then like parentheses linked by peptide bonds via condensation reaction from carboxyl group the COOH to the amine group or amino group, doesn't matter, which is the N minus NH. Oh no, no minus. Why did I write that? Stupid, I'm sorry. NH3. Boop. Oh, okay, double parentheses, sorry. So it's a sequence of amino acids, parentheses, linked by peptide bonds via condensation reaction of the carboxyl group to the amino group in a polypeptide. Woof. Structure is determined by and this is very important, the sequence of DNA bases of the gene that codes for that polypeptide. Because remember, your information is going from DNA to RNA, there's several of them, we'll talk about them later, to protein. And it's your every 3 amino acids in DNA, or I'm sorry, every 3 nitrogen bases in DNA is a codon in RNA. And then your sequence of codons tells you what amino acids are made. I guess we'll put that down. So 3 nucleotides goes to whoa, 1 codon, which goes to 1 amino acid. Ta-da! E! And so here you can see a huge string of them. They have this little sample section where they break out these 3 and show you what they would look like. I don't like that they didn't draw out the R groups. It's kind of annoying, but it is what it is. And then down here they give you a little check for understanding. They ask you how many amino acids are in this peptide. It kind of bothers me a little bit because they have these 2 that are cut off, and like I don't know if we should count them or not. I think for the purposes of keeping my sanity, I'm not going to count them because it's going to bother me because, like, what do they mean? So we're going to focus on this highlighted area because it's going to annoy me if we count in the little halvesies ones. If I would have noticed this prior to printing this packet, I would have fixed it, but I didn't notice. And so we'll just look at these ones. We'll ignore the weird halvesies ones because they're not important. Oh, shoot. I got part of the halvesies one. Okay. I'm annoyed. I'm not restarting. It is what it is. It's fine. So if we were to count them, you can either start at the NH group, or you can start at the COO group. Because we're cutting off this weird halvesies one and this weird halvesies one, we're going to start at the COO. So that's the start of 1. That's not showing up well. Jessica, listen. All right, striped purple. Oh my God, that's worse. This is why these take me so long. Okay, we'll do black. So there's the start of 1. You go COO, boop, 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 boop. Then you see your N. That's the stop. So that's 1. COO, boop, 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 N. That's our stop. That's 2. COO, boop, 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 N. That's 3. COO. It gets weirdly cut off, so we're not counting her. So 3. 3 if you don't count the weird halvesies ones. 5 if you do. Okay? Cool. On to the next page. Looking at secondary structures. Get out of the way. So, secondary structure. And so secondary structure is held together by hydrogen bonds. Oh, geez, I should have gotten all the colors out. I should have known. Held together by, hydrogen bonds between the oxygen of your carboxyl group and the hydrogen of your amine groups. And the polypeptide backbone, which is just your polypeptide chain. That's all that means. And so, what are the 2 most common secondary structure motifs? These are going to be, I'm not going to write in yellow. We'll write in orange. Your alpha helixes. And your beta pleated sheets. Do you remember that the beta is the pleated sheets? You can think B for beta pleated sheets, B for bed sheets, if that helps. In diagrams, your alpha helices are usually shown as the little curlicues, and the beta pleated sheets are usually just flat arrows with like a little bit of a weird twist to them. If you're looking at like the cartoon version of the diagram, I'm going to assign each of them a separate color. We'll do alpha helix can be purple from this moment forward. And beta pleated sheet can be whatever this is. What color is this? No, I'm not going to do that. The color looks gross. We'll do blue. Listen, I got a new set of highlighters because my other ones were getting crusty. I don't know how I feel about them. Some of the colors are better. Some of them are worse. Why did they give me gray? And so beta pleated sheet is now blue. Oh, blue for beta sheet. This worked out. Scooch. And alpha helix from this point forward is now purple. P for alpha helix sheet. Okay, the titles are gonna have to get cut off. That's fine. Bump ba dump. Scooch. Alrighty. So key things. We'll do beta pleated sheet first. Beta pleated sheet has your amino acid chain. Connected laterally. Laterally is kind of like horizontally, but you might not always see them oriented this way. And so rather than think of laterally as horizontally, you could think of it like laterally. Because it looks like a ladder. With your two amino acid chains, and then your rungs being the hydrogen bonds. H bonds. AA chain. And they're also usually minimum 2 to 3 hydrogen bonds. Forming a usually twisted sheet. Usually twisted, pleated sheet. And pleated is just like the wrinklies. Think like a pleated shirt. And so then in our pleated sheet, we'll highlight the backbone in blue. Ew, I regret picking brown for hydrogen bonds. Oh well. And we'll highlight our hydrogen bonds in brown. And as you can see, they are always connected by oxygen of your carboxyl group, H of your amino group. Okay. On to alpha helix. Your alpha helix, oh shoot, I need to get out the purple. That purple does not show up. We're using the dark purple. They're a right-handed coiled spiral. Right-handed just describes like the direction. A fun fact about Ms. White, I am really bad at my rights and lefts, so don't ever ask me what direction a right-handed spiral is. It's this way. Okay? And so this is going to be weird to explain, and I think that seeing it in the picture will make it make more sense. But every backbone NH group forms in a hydrogen bond to the backbone. CO group. 4 residues or like places earlier in the chain. Yeah, I know. In words, it's a little confusing, but let me show you what it actually means. So, first, let's highlight all of our hydrogen bonds. Where's the brown? This is so unfortunate. It's okay. So, 1 hydrogen bond, 2 hydrogen bond, 3 hydrogen bond, 4 hydrogen bond, 5 hydrogen bond, 6 hydrogen bond. Okay. So, when you're looking at this, one, 2, 3, 4. 1, 2, 3, 4. The short ones, the places are condensed. It's weird. Just know it's 4, okay? The short ones are condensed because it's a picture. It's hard to explain. Just know it's 4. They connect like that. It's what gives them the coiling. Yeah, I'm sorry. I don't have a better way to explain it because the way that this picture is drawn, like, it's just weird. Yeah. But it should be 4. These 2 are good representations. Like, if we make this one example A, this would be A1, A2, A3, A4. Good. If we make this one, hello? Example B, B1, B2, B3, B4. The short ones I have no explanation for. I don't know why they look like that. I think the picture's just drawn weird. Because it should be like these 2, and I guess this one. But these ones, I think it's just the picture being scaled weird. Alrighty. Talking about tertiary structure next. What color do we make tertiary structure? Green. Tertiary structure. So tertiary structure is the folding of a single protein, that's what differentiates it from quaternary structure, into a 3D structure. So now we're looking at 3D things. 3D structure gives proteins their functional properties, such as active sites on enzymes. That's why they can have that little puzzle-like shape, lock and key. And so we have a couple different types of bonds that go along with our tertiary structure. And so your tertiary structure can be made up of multiple different types of secondary structures. So this is one tertiary structure. Your tertiary structure is the folding of a whole polypeptide chain. It's stabilized by interactions between the R groups of your amino acids. And so for funsies, let's locate our alpha helices. There's one in the back. And our beta pleated sheets. Oh, they're gonna overlap. Oh no. Okay, it's fine, I guess. And then this is obviously a 2D depiction of a 3D structure. So imagine that this backbone here is in 3D. And then we have our 4 different types of bonds that we can look at. There's obviously more, like there's also van der Waals forces, there's hydrophilic interactions, but these are the 4 that you'll most commonly see and that IB expects you to know on like a slightly more intense level. Get my little cheaty sheet out. Scooch. Okay. Let's give each one of these a color. Okay, we're gonna skip yellow and skip brown. So, and we can't use green either, so we already used green. Alright, we'll use weird red for hydrogen bonds. Hydrogen bonds get to be weird red. Dun, 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 dun. We'll use, oh, I'm gonna have to reuse colors, that's fine. We'll make ionic bonds. This, which I think is also kind of weird red. Yep. We'll make ionic bonds this version of weird red. Oh, it's gonna be, okay, it's fine. We'll make disulfide bridge. Okay, disulfide bridge, I guess you can be blue. No relation to this. Disulfide bridge, where are you? There you are. Do 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 do. Do do do. And then, last but not least, hydrophobic interactions are gonna be purple. There we go. Oh, polypeptide backbone feels like it needs a color. We'll make it green. Dun, 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 dun. Dun, na, 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 la, 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 la. And ta-da! Oh, we're not gonna do the backbone on these ones too, otherwise it's gonna make me upset. Gosh darn it. Alright. Oh, okay. A little twisty one. Okay, this was really a choice of shape. Alrighty. There we go. Much more exciting. Okay, so for, oh, well now, okay, this one can be pink, this one can be red. So for your hydrogen bonding, it occurs between your polar R groups It follows your same rules of electronegativity that we had when we talked about hydrogen bonding and water. And they are weak bonds. Click. Your disulfide bridges, per the name, di meaning two, sulfide meaning sulfur. They are between two sulfur containing water groups, which is like primarily just cytosine. So that's one way that you can identify these. If you ever see the double S's, or if you see that it's cytosine as the amino acid, you pretty much know it's a disulfide bridge. These are also really strong. So like if something is breaking these or reforming these, it is a strong reaction. Whatever is going on is very heavily changing the protein. Your ionic bonds. Ions, they are just charged molecules, which makes sense because your ionic bonds are forming between oppositely charged R groups or ions because they attract and form ionic bonds. This is heavily charge dependent. So if pH changes, bonds are going to change. Because remember, having a low pH or being acidic just means that you have a lot of like positive hydrogens floating around that could in turn bind to the negatively charged ions in that protein and therefore cause it to not make these ionic bonds. Boop, 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 boop. Your high pHs or your basic things just have a lot of your negative OH groups floating around in them, which means that they could bond to your positively charged molecules in here and cause them not to bond to your negatively charged molecules, and therefore the bonds within that protein wouldn't form and it would change the shape. Which is why when we put proteins in extremely low or extremely high pH conditions that they're not typically in, they get denatured or they change shape. Hence what happened with the albumin. I was trying to explain that earlier today, but I really feel like I did not do a good job. So, my apologies. I was talking to Sophia, I'm sorry. And then the last one is your hydrophobic interactions, where your amino or your nonpolar amino acids orient towards the center, form a little pocket of protection. To avoid water around protein. In turn, hydrophilic amino acids tend to be on the outside. This again is dependent on the solvent. An amino acid in oil is going to form a different, or I guess a protein in oil is going to form a slightly different shape than a protein in water because it's folding based on the conditions it's in. And so your hydrophobic amino acids, if you put it in oil, is going to want to go outward, whereas your hydrophilic ones are going to want to go inward because of the polarity. And so it is solvent dependent. This is another way that you can look at denaturing proteins. This is also really weak interactions. So they tend to be the ones that will change or shift. And that is your summary of all of your interactions. On to the next page. Our last type, your quaternary structure. Oh no, I lied. We have to talk about channel proteins first. I'm sorry, I didn't mean to lie to you. Channel proteins and then quaternary structure. So, channel proteins. The effects of polar and nonpolar amino acids on tertiary structure of proteins. So tertiary structure. We're gonna make polar areas blue, and nonpolar areas will be the ugly red. Go away. Oh my god. Because blue is water. I don't know. And so, looking at amino acids and proteins can be nonpolar, and therefore hydrophobic, or polar charged, and therefore hydrophilic. And this affects how their structures embed within your cell membrane. Remember your phospholipid bilayer from when we talked about lipids? It has that, it has that structure where it has your heads, your tails, your heads, your tails, where your nonpolar tails, boop, boop, are in the middle, and your polar heads are on the outside. And so when we're looking at things like channel proteins, and integral proteins, they have to adapt where their hydrophilic and hydrophobic, or polar and nonpolar areas of those proteins are in order to be able to work within the membrane. So if we imagine our cell membrane, where we have our heads, that are polar, that's why they're blue, and our tails, that are nonpolar, that's why they're red. And then if you remember from lipids and carbohydrates, things like water can occasionally pass through easily because they're so small, but things like charged particles and ions can't get through your membrane because although they can get to the surface, they can't go through that hydrophobic area because they are so polar. And so in order to combat that, your cell has these special channel proteins that allow for them to pass through. And so when we're looking at this diagram, here's how this whole deal works. Your polar, your polar / hydrophilic areas of your protein line the inside of the channel to allow water and charged particles to enter / exit the cell. And so anything that's typically polar can now move in and out. And so that area would be like this area of your protein. Oh, it's hard to see the little outline of this protein, but it's like another little alpha helix there, but there is like supposed to be like a little squiggly deal here. It didn't copy very well. There you go. There's your little protein squiggly. And so then polar can go through. Polar particles. Your nonpolar hydrophilic oh my gosh, hydrophobic. Gosh darn it, Jessica. That's phobic. Oh my god. Your nonpolar hydrophobic line the outside. To like stabilize and secure that channel in the membrane. It's like the glue, or like an anchor. Where's the ugly bread? Ah, almost dropped the ugly bread. Okay, here's the ugly bread. Beautiful. And so polar to polar, nonpolar to nonpolar, hydrophilic to hydrophilic, hydrophobic to hydrophobic. Integral proteins, very similar. Again, you can't really see the little, I guess this one doesn't really have an outline, so it's fine. I'll leave it. I won't bother it. But so you have your heads. Polar, hydrophilic, your tails, which are nonpolar, hydrophobic. I'm annoyed. I'm annoyed that I messed this up so bad. And so on this one, similar thing, your nonpolar, hydrophobic area is inside the membrane. To hold it in place. Ba, 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 ba. Eee. And your polar hydrophilic area is outside the cell and inside the cell. Because it can be in the aqueous solution. And it usually will interact with things inside and outside of the cell. Whether it's binding different stuff, acting as an enzyme, all kinds of things. There we go. Beautiful. It looks very American. Alright, finally, last but not least, quaternary structure. What color was quaternary? Oh, it's blue again. Gosh darn it. Okay, whatever. So quaternary structure. Bum-ba-da-dum. Key things about quaternary structure is that the structure contains more than one polypeptide, and it simply is just different polypeptides arranged together. In general, the same type of interactions that contribute to tertiary structure also contribute to quaternary structure. There are also conjugated quaternary structures which have additional like non-protein things to help hold them together. We'll talk about that in just a bit. Okay, if I have to look at this blue again, I think I'm gonna lose my mind. So, oh, I have to do quaternary structure again. No, I swear to you, this blue keeps coming back to haunt me. Okay, it's fine. I'm just tired of it. I'm tired of looking at it. And so our two main types are non-conjugated and conjugated. Which we'll look at more on the next page. Bum-ba-da-da. Alrighty. Flip. Nope. Not flip. I lied. My other page is over here. Okay. So for conjugated, it's hemoglobin. So we'll make it red. The other one's insulin, which to me is also red, but that'll be green. No, we'll do green for fibrous. Okay, it'll be purple. So conjugated proteins. Bum-ba-da-dum. Your example is hemoglobin. This is I think a European way of spelling it. Biggest thing is that it has these heme groups. That's what makes it conjugated. It is really hard to see them in this picture, but they are there. They're like little discs in there. There should be 4 of them. On my life, I cannot see them on this side. Yeah, I don't know where they're supposed to be over here. Maybe I can find it. I have this picture in color. Hang on. Let's see if we can find them. Little scavenger hunt. No. No chance. Here's here. Here. I thought it was there, but no, it's here. And there. Nightmare. Okay, well there they are. It's really hard to see them. Okay, anyway, let me focus. So conjugated just means that it has one or more non-polypeptide subunits. So these can be lots of things. They can be things like zinc. They can be things like activators that bind to proteins in order to help modify the shape for the substrate. In the case of hemoglobin, it's like an iron-based group. And so their main goal when you have these subunits is that they increase chemical and functional diversity of proteins. It allows your proteins to go beyond CHON. And by going beyond, they end up having the ability to have more diverse functions in the body. Like the reason that hemoglobin is so good at carrying oxygen is because it's able to have this iron group here. It's also why a lot of your enzymes are able to function. So it's common in enzymes. Your example, hemoglobin. It's 4 polypeptides. Plus 4 iron-based heme groups. Your non-conjugated ones, the examples they give you are insulin, which we are all hopefully very familiar with, and collagen. In this picture, though, it high-key looks like insulin has the groups. I know it doesn't, but like the way that they drew this, questionable. Anyway, it is just only polypeptides. Nothing else. And they're bound by the same interactions. Interactions in tertiary structures. Your examples are insulin, which hopefully we all know by now is 2 polypeptides and disulfide bonds. And collagen, which is 3 polypeptides, like held together literally by how they're braided together. Ta-da! All right, last thing we have to talk about is the difference between fibrous proteins and globular proteins. We will make fibrous proteins green. Globular proteins, just because I hate the word globular, they're going to be brown. Losers. That's not nice. Globular proteins are very useful. I just think it's a stupid word. But let's make this chart look nicer. Till I'm tired. It's very late. When you get the inevitable remind message telling you that this video has been uploaded, that's when I left work. Alright, oh, it's like Shrek themed. Okay. So, fibrous proteins. Shape and structure. They are rope-like, hence fiber. Think fiber. Like fabric fiber, not like fiber that you eat and then poop. So they're rope-like. They have no folding up in tertiary. So they don't like blob up when they're in tertiary. They are elongated. They typically have no alpha helix. And they are narrow fibers and filaments. I'll try to draw one momentarily. Solubility in water, they are insoluble. They're function, they're usually structural. They provide support. They have high tensile strength. There's a lot of variation. They're usually in skin, tendons, ligaments, cartilage, cartilage, basement membranes, your cornea, hair. Key examples: collagen. That's the big one that IB really wants you to know. And then keratin and elastin. Which isn't skin. Woof. Scooch. Where's Brown? Okay. Globular proteins. They're blobby. They're blobby globby. They have a rounded shape. They have folding in tertiary. They fold up in tertiary. Because they have many bonds in their R groups. Many bonds between R groups. Lots of those interactions. They are soluble in water. They're often involved with ligand binding. Often involved with ligand binding, which is used a lot in drugs and pharmaceuticals. Their transport proteins. Think that blobby shape, it can pass through blood vessels and stuff very easily. They're used in your immune system. Immunoglobulins, it's in the name. They're also your membrane proteins. All globbed up there. Your key examples: hemoglobin, insulin, enzymes. Oh, fun one, albumin. Oh, let's draw I forgot to draw them. Let's draw a little globby boy. Blah, 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 blah. Globby. We can also draw a channel protein. Ooh. Uh-oh. Okay. Well. Alright, we'll draw an enzyme. There's the substrate. Okay. Oh, wait, hang on, wait. I forgot to draw the Brady one. On my paper, I drew a really grody one, so we're going to do it differently. Okay, so here's we'll do collagen. Here's strand 1. Whoa, look at collagen go. Ah, strand 2. Ooh, collagen. Oh my gosh. That's strand 3. Where does this part go? How does a braid work? Alright. Ooh. Look at collagen all braided together. Oh my gosh, crazy. Alright. I'm done. That's it.